Okay, good morning, ladies and gentlemen. I'm very glad to stay here and having the opportunity to have the first talk in that session. So there are a lot of very interesting technical talks over the days. So in my talk, I will not focus on the technical details of devices or packaging technology, which is presenting the next one. I will focus on requirements and market aspects. And since I'm from Bosch, I will focus on automotive requirements for sure. First of all, I would like to give you some insights why it's important to have electronics in e-mobility and what are the driving forces to that. And then I will focus on the inverter. I will tell you later why on inverter, and looking at the switching behavior, braking conditions, and something like that. But that's not a complete story. So I also will look what else is decisive for being successful beside the power devices, and what kind of boundary conditions are necessary to have a market success story. So first of all, I will focus on silicon carbide. Why silicon carbide first? Since that's a material which is in place already in the market. So all the feedbacks we get from the market, from the application, is mainly focused on silicon carbide. A lot of these aspects, however, are transferable to other wideband or ultra wideband semiconductors as well. So let's first have a look on the market distribution of silicon carbide. When you look on the left-hand picture, you see the market is strongly increasing, but the main market is automotive. So that means that's the reason why I'm talking about automotive. That's the market for silicon carbide. And when you zoom into this market, you see what kind of application is more or less driving that story. That's the inverter. And it's quite simple. Why is the inverter? Since the inverter is the device in the car handling the biggest power, and with that having the biggest chips, having the biggest amount of wafers, so that from the market point of view, that's the most interesting application. That's the reason I'm focusing on that application on today. What are the trends here within the battery electric vehicles? So there are several trends. One is, for example, the integration. That means there is no machine and inverter and converter separated. There's a tendency to integrate it into one package. That's the ECSEL. That means there's a three-in-one solution, very easy for the OEMs to handle these devices, and they have one device to put into the car. A low degree of integration, that's a Charcon, that's a combination of charger and converter, which also uses one housing and makes the application much more simpler. When you look at the trends of the voltage, some years ago, there was a clear tendency that the voltage is around 400 volts, and there are some exotic devices using 800. That picture has completely changed. So meanwhile, 800 volt application and 400 volt application are more or less on eye level. That means you have two markets. That means using two voltage classes also on the device level. Actually, when you look into the market, up to 75%, meanwhile, are based on silicon carbide. And when you look especially at the 800 volt, it's already reaching 100%. But that means wide band gaps. In that case, silicon carbide has reached its application in automotive. Here you see some example of our last inverter generation. It's a 2 voltage class version. And just to give you a feeling what we are talking about, we're talking about more than 600 amps in the 400 volt generation, and talking about some 500 volt amps in the 800 volt version that ends up with powers in the region of 170 to 260 kilowatts. So when you now look into the history, you see that when you start with the first generation in 2010 and end up with the, let's say, actual generation, there's a continuous trend increasing the powers. So there's no, let's say, saturation. You always want to have higher powers. So what are now the requirements for such an inverter? I think you are familiar with pictures like that. Here you see that automotive inverter application is located here in the field where silicon carbide and silicon IGBTs are overlapping. And it's working at moderate frequencies, and that the high switching applications for onboard chargers are here in the bottom, the gallium nitride and silicon carbide working at higher frequencies. This picture suggests that the application of inverter is dominated by the static losses, and switching is not that important. I will show you on the next slide that that's not the case. Even also for the inverter, switching is very important. When you see here, what are the requirements starting at the customers, you see the power requirements for acceleration, you see charging time, and you see one of the most important requirements is range of the vehicle. And when you break it down over the powertrain system down to the components, you see that the efficiency is the most important requirement for such wideband semiconductors within the automotive inverter application. And you will have a more detailed look into this efficiency. You see on the left-hand side a comparison between an IGBT solution and a SiC solution. And within the driving cycle, that means NEDC or WLTP, you see up to 8% efficiency improvement, depending on the electrical motor, when using silicon carbide instead of silicon. So I think that's quite well known. But when you look a little bit deeper, what is about the losses in that situation? You see on the right-hand side the losses of silicon carbide in this switching application, and you see that it's mainly due to switching losses. That means in inverter application, it's all about efficiency, and in the efficiency, it's mainly dominated by switching losses. And that means not only high frequency application are sensitive to switching losses, also these, let's say, moderate switching applications live from a good switching performance. Since it's the case, I would like to spend a few minutes going a little bit more into detail. Where are the switching losses coming from? What's going on during a switching process? And here on the right-hand side, you see an equivalent circuit of a half bridge. The high side transistor represented by a diode and its output capacitance, and the low side transistor with its parasitic elements representing the switched device. And here you see the current and voltage conditions. Now the transistor is switched off. The current is flowing here through that diode. That's more or less, for example, at the dead time of an inverter, a situation before switching on the low part. When you look now into the next timing step, we start to switch on the gate. The current is still flowing here, and the gate voltage is rising. You have a rectangular shape, which tries to increase the voltage here on the transistor, and the time constant is defined by the gate resistance on the one hand side and the input capacitance, so the gate source capacitance on the other hand side. That means when you want to try to switch it on very fast, you can do both things. You can decrease the resistance, or you can decrease the input capacitance. So for silicon carbide, you have usually very high capacitance here. It's very easy to moderate the switching speed by the gate resistance. It's not the case with HEMTs, where the gate charge is very low, so it's quite harder to control the switching speed by that resistor. Next step, the voltage increases, and now the channel starts to open. What's happening here is the diodes, minority carrier, are flowing through that channel, and the channel current is now giving a voltage feedback to the gate loop. That means this current, in combination with the inductance, reduces the switching speed. That means here on that diagram, you have still high voltage, but the current is increasing, and that dotted line here shows the aspect of the minority carrier here. That means also in that case, the transistor has to carry the diode capability of the other transistor. That means it's also necessary that the minority carrier charge of that transistor is pretty low. Otherwise, it has to be handled here. Next step. Now the commutation takes place. That means the diode blocks. The capacitor, that part, starts to be loaded. And now the voltage increases here. That means the emitter capacitance, so that the capacitance between drain and gate starts to be discharged. And that means that the current is flowing to that node here, overlaying the current coming from the driver. And you see that here at the gate, that there's a dip in the gate voltage. And this dip is depending on the size of that capacitor. That means if you do it wrong and you have a too big capacitor, that peak goes down and switches the transistor off once again. So that's also a design element for moderating the switching, that you have a low feedback on the capacitor. So the voltage slope, the dV over dt, is from that defined by this capacitor, and compared to silicon, it's very small in silicon carbide, but nevertheless, compared within the silicon carbide device itself, there are huge differences moderating this voltage. That means when you go on that diagram, you go now here, reduce on a specific current, but reducing the voltage. Next step. Everything is more or less in a stable situation. The voltage of the gate is still rising. That means reducing the RDS on, and the current is flowing through the transistor. In that case, the switching on process is closed, and the switching losses here are determined by the transients of the voltage and the current. That means I showed before how you can manage them. That means you can reduce the overlap of current and voltage by the parasitic elements. When you now look at the turn-off process, the same story. The current is flowing here through the transistor. The diode is passive here, and you now start to decrease the gate voltage. That means going from 20 volt to -5 volt. And now you have the same story. You have to discharge this gate capacitor through gate resistance, which can be a different one, not be the same, and also discharge the next emitter capacitance here. Next step is you decrease the gate voltage more and more, and now the capacitance will come into the play of the transistor here itself. So here you see that the same story starts. The emitter capacitance slows down the change of the gate voltage up to that point that the transistor switch on once again, which is not wanted. So also the emitter capacitance has to be designed very carefully, especially in correlation to the gate capacitance. But in this situation, the drain source current is split into 3 parts. One part is the discharge of emitter capacitance. The second part is the channel current, and the third part is the current through the output capacitance. And that means, since at the beginning, that means when the transistor is open, the capacitance is voltage here is more or less at 0 volts. The capacitance is very high. That means most of the current is flowing into the capacitor, and that means the current is constant and the voltage is more or less pinned by that capacitance. And the next step, this capacitance is still charged. But now the current is going down more and more. You see that now the capacitance values are reduced due to the higher voltages. And the consequence is that in the first step, the current of the transistor and the channel is already switched off. That means ohmic losses are more or less switched off. But still the current is flowing here into that device, so that In that diagram, you have a curve which is overlapping, but the omega current is going down very fast. The real current flowing here in is going into that capacitor. And that means that the real losses are dramatically reduced, and you have more or less the energy start into that capacitor. And that has a good and a bad aspect. The good aspect is you don't have really losses. You could use this energy stored here in the next step. Bad news, in the inverter application is exactly the charge of the capacitor I showed before, so it's burned in the switching off phase of the next transistor switch. When you, however, can put this charge into an inductance, like this done in a resonant application, you will have dramatically reduced losses during that switch-off period, since that are not really losses, but it's stored energy. So that means in that case, you have more or less zero losses for the switching off behavior, but it's a problem to use this energy in the next step in hard switching application. You can only do it with soft switching. When you go to the last step, you see also the other parasitic elements, like the inductance in combination with the capacitance, give rise to ringing. That's more or less also the influence that the other elements coming from the packaging have influences to the switching behavior, but more indirectly to the real losses. So summing up that switching behavior, you have the turn on, and more or less comparable currents. The turn on losses are much higher in silicon carbide devices compared to the turn off losses. And this turn on energy or this turn on losses are dominant in the partial and high load application, since they are directly proportional to the currents. As I said before, it's depending on the transients of the current and the voltages, how much losses are showing up, and they are directly proportional to the current. The turn off losses, they are lower, but they are not depending on the current. That means they play a role, especially when the current is low. That means due to its capacitant load here, it's only depending on the output capacitance and the voltage, which voltage is fixed, so you can also play with the output capacitance, and it's not depending on the current anymore. That means the switching behavior is very important for the efficiency of the inverter, and that switching behavior is more or less defined by the parasitic elements of such a transistor. It's not by others. It's only a little bit about the GM and so on. It's mainly the parasitics. And since the parasitics are parasitics, they cannot be designed freely. So you have to find an optimum between the, let's say, static functions, conduction, flowing and blocking of the devices, and these parasitic devices. Okay, so we talked a little bit about switching. There are some other conditions which are very hard for the devices in this automotive application, and they are called special operating conditions. One requirement is when there is some problem with the electronics, whatever, in a car, you have to switch off the electronics, and the engine is still running. So there's energy coming from the rotation of the engine, and in that case, in a permanent excited synchronous machine, the voltage would rise infinitely if you don't take any care about getting rid of that energy stored in the magnetics. And usually that's done by shortening the half bridge on the upper or the lower side of all three phases. And that gives rise to a current flow shown here on the right-hand side with extremely high currents, but in combination with quite long times. So we are talking about milliseconds. And as you know, milliseconds for a semiconductor it's forever. So these conditions are more or less a combination between the semiconductor and the packaging design in order to get rid of the millisecond pulses of that energy. What does it mean? We're talking about the current densities around 20 amps, which is usually 3 times the nominal current showing up for the first times. So this event, it's a special operating condition so that it's taking place several times during lifetime, but not as a continuous condition. But devices have to survive this condition as well. And as an active controlled manner, that means a device designed for a nominal current has also to be functional with 3 times nominal current for that specific timing. That situation correlates to another problem. When you have these transistors, usually 2 of these transistors are in the turn on. That means current flowing through the channel, but one is flowing backwards. That means in a MOS transistor, current flowing through the diode, or if you don't have a MOS transistor in silicon carbide, you have a silicon carbide diode. And this reverse current usually is very critical for the PN junctions. The PN junction in these very high current conditions tend to have a risk of bipolar degradation. That means this high current density initiates crystal defects to grow, and with that, increasing the resistance of the transistor. And because the resistance is increased, the temperature rises up, so that's more or less a self-feeding feedback process. Also, in that case, the transistors have to be designed that this overcurrent through the diode can be handled without having diode problems. By far the harshest requirement for the transistors, however, is the bridge shortening event. That means you have a complete shortening of those transistors, either by misfiring of the gates or by some, let's say, electrical connections here at that phase point, that giving rise to extremely high currents. Extremely high currents means in typical devices we are talking about several kiloamps. And since that's in the saturation regime of the transistor, the voltage is even high, ending up with losses in the range of megawatts. That means the devices will not survive that very long, but they have to survive it for a significant time. And you see here, there are 3, let's say, timing blocks. The shortest one is the reaction time of the driver, so he does it very fast. You have a time period which the device itself needs to switch off. Talked about the timing and the switching behavior at the beginning, so that's also some several tenths of nanoseconds. But the longest time is needed to detect that short circuit event. And that is more or less due to the fact that the active short circuit is a, let's say, wanted effect, and it's not that short circuit effect. And you have exceeded at least 3 times nominal current. And after reaching 3 times nominal current, the detection starts to say, okay, that's now a bridge current or bridge shortening event, and now you switch off. That means you have to wait, see if the current is increasing already, but you can't shut off because you don't know whether it's an active short circuit or whether it's a short circuit by that accident. That has to be designed now in that way that the saturation current of the devices is limited by additional elements. And usually that's done by designing the, let's say, parasitic JFET transistor and a MOSFET in that way that this transistor or this design element reduces the current, the saturation current, but trying to keep the RDS on as low as possible. But it's always a trade-off. That means you have always to find a trade-off between the minimum short circuit robustness you can accept and the others on. So I showed you now that there are a lot of aspects, contradicting aspects, which has to be also optimized. And that can't be done by hand anymore. So you can't sit on your TCAD and design a device looking at RDS on whatever. You have to do a multi-purpose optimization. And to achieve that, we have built at Bosch a system where you start with calibrated silicon carbide models. And then you create building blocks based on a specific device design. you modify doping profiles, you modify geometries, and set up a library with different, let's call it, design elements or building blocks of the device. And now you construct meta models of these devices and combine now with multi-purpose optimization, trying to find the optimum for all the parameters I mentioned before. That means the JFET resistance, the RDS on, the capacitance, and whatever, in order to fulfill the different application I showed before. This system we have in place at Bosch since several years, and with that we optimized our different generation we have in place now from one generation to the next by double-digit numbers. So here you see from generation 1 to generation 2, for example, the optimization of the RDS on. But on the other hand, on the right-hand side, you see that we also could improve the trade-off between RDS on and short-circuit robustness. So we could improve that trade-off curve to make it steeper, meaning paying less RDS on to get more short-circuit robustness. And that's more or less a result of that design optimization we did put it to. Okay, what's going on the inverter level besides that what I said before? So usually the approach to save energy is the two-level topology. That means there's a PWM modulation switching on and switching off device between the DC-link voltage and zero voltage. This is the typical topology which is used in all the inverters actually on the market. The problem is that you have to pay quite big silicon carbide areas, which is quite expensive. And since mostly the efficiency benefit from silicon carbide shows up in the partial load, that means having the benefit of the switching events I showed before, but also having the benefit of having a MOSFET instead of the diode characteristics of an IGBT. The MOSFET is only very effective in lower and partial load, and at the high load you could use an IGBT, which has a much better current handling capability. And there are some tendencies, or also driven by Tesla, to use that double system IGBT combined with the silicon carbide. It has some requirements for the drivers, so it can't be used optimized by the same driver concept. But that's some trend we see actually in the market. Another trend, it's not very new, but it's coming up every few years, it's a multi-level topology. Well, the benefit of a multi-level topology usually is a three-level topology. That means you have not a switching between zero and the complete DC link voltage. You have two steps, DC link voltage half and DC link voltage full. And this step reduces the dV over dt. That means having EMI advantages on the one hand side, but also with these EMI advantages, having lower losses of the harmonics and the electrical motor. From that way, coming with some benefits in additionally reducing the switching losses within the topology without modifying the semiconductor devices. So what's going on here? What's the trend will win at the end of the day is what we show in the next generations. So I talked a lot about the transistors and the devices and the topology. What else is important here? There's a driver. So when you have a module in an inverter, it's not usually it's not one transistor. It's a parallelization of up to 7 transistors, for example. So the transistors usually don't have exactly the same parameters. So you have situations where one transistor is morely switching on and the others are not switched on already. So one is carrying the most of the load. And when you see here on the left-hand side of the situation, you see that the losses in that transistor, which is carrying the most of the load, is much higher. So we have to design the area the cooling. So you have to design the system and the semiconductor area addressing that situation. That means you have an over-design due to the unbalanced situation in the module or the scattering of the parameters. That means when you have such a situation and you have one gate switching on all of the transistors, you only can over-design to have a safe operating situation. When you have a gate driver, which drives every gate individually, you can, let's say, address that situation and reduce the load on the transistor, which is with lower RDS on, for example, in that way that you get a load balance. And that means the balance of every transistor is more or less the same, and you can reduce the chip size with that. So spending some more intelligence into the driver saves a lot of area in the very expensive wide bandgap semiconductor field. And that's we have addressed with a specific gate driver, which is optimized for the parallelization of silicon carbide devices. That means when you will be successful with silicon carbide devices, you have also to look at the drivers, and not only in the driver, let's say, functionality in the classical manner, but also to address that parallelization. There's a simple picture to show what else is important, which I will not address too much, since it's also addressed in some talks within that session, to reduce the losses. So the blue ones, the yellow ones, that are the fixed parameters coming from the system, which can't be modified. But the blue ones, they can be modified. The RDS on, I said already, that's the typical optimization you have within a transistor to reduce that. But also the packaging losses. I just mentioned the word of copper. Is a factor which is already addressed now to reduce, for example, copper metallization losses in the chip. We talked about that losses due to switching, and here also the inductance is a very important aspect I showed before, since it slows down the switching speed. That means reducing parasitic inductance is one key feature. Sure. And cooling, that's the last one. For sure, the devices are designed to operate at the maximum junction temperature. When you can increase the junction temperature by more stable electronics, you can, let's say, reduce the chip size, and when you have a better cooling with the same mechanism. So beside the device, you have a lot of more, let's say, tricks to optimize the module design. So what else? So we have talked about the devices. We talked about some, let's say, peripheral aspects. What's else necessary to make a success story from that semiconductor? So when you look here about the elements, you see at least three elements. One is that what we have talked before, that are the end-to-wheel losses or the complete loss of the efficiency story topic. But when you're talking about silicon carbide especially, but also some other wide bandgap semiconductors are going more or less the same way. The substrates play an important role on two levels. First off, the cost itself. That means the high substrate costs compared to silicon-based are a significant part of the complete inverted costs. And on the other hand, you have a yield impact. So usually these expensive substrates are not that good. So that means they also reduce the yield, and with that increasing the cost once again. That means being a successful market means also to handle the substrate situation. And in silicon carbide, it's for sure, but in gallium nitride, you see that there are also gallium nitride substrates are going the same way, like silicon carbide being very expensive. Also, the engineered substrate, like the QST, for example, they are less expensive, like the gallium nitride or silicon carbide, but even much more expensive than silicon. That means also in that way, these two columns are important. And with the engineered substrate, especially the right-hand column is important. That means the defects are reducing clear. That means handling the substrate is an important story. When you see here what's going on, we have, besides that defect story, also the availability story. That means where do the substrate come from. Good news, when you look at silicon carbide, within 2 years or 3 years, you see a huge improvement in quality. That's the story when the market pushes and a lot of companies are entering that market. You can expect that a lot of improvements can take place. And especially the Chinese companies are here very successful in developing high quality substrate in a very short time. But that's actually the other side of that story. So you're focusing a lot of the substrate market within one region. And that's also, as we learned in the last months, unstable situation. That means also the excess of high quality substrates over the different region is a very important part to having the successful technology in place. To address that, as I mentioned before already, there are some aspects going on. In Transform Soitec, for example, developed their smart card technology. There are other technologies going on with the laser split and so on. So that means, beside that, there are activities going on to get rid of that problem of that substrate quality by clever approaches, splitting a high quality level of material and putting it on a, let's say, cheaper or even from the physical kinds of view, better suited substrate. And that means we get rid of that problem that we have to have a big amount of the substrate. We just have to have these layers, and we can optimize, engineer the quality. And we did it, for example, together with Soitec and other companies with polysilicon carbide. And we saw that we at first could reduce the resistance of the devices without modifying the devices, that we can simplify the process flow without modifying the devices, and that we even get better stabilities without modifying the devices. That means besides optimizing the devices in wide band gaps, the substrate play a much more important role than it does in silicon. Okay, coming to the conclusion, summer. I showed you that the automotive market for wide bandgap semiconductors will be the most important one due to the high powers handled there and due to the big wafer numbers necessary for doing that. As you look in the press releases, you will find every 2 months a new company announcing that they increase the silicon carbide capacity, that they're building out new capacities for silicon carbide. So all driven by e-mobility. It's all about efficiency, that's the topic. That means the efficiency of the devices is a motivation to use silicon carbide. Since silicon carbide is more expensive, it's not that mature than silicon. The only way is to have better efficiency in the system. And that efficiency is dominated by switching losses. I showed you that it's not as usually implicated the RDS on, it's switching. So improved switching probability is the key to have successful devices. The challenge is, however, it's not the normal operation, it's special operation conditions. So they decide the size of the devices, the complexity of the devices, and that has to be taken into account also in the research on new device concept, checking whether these special operating conditions can be addressed or not. Let's say system optimization can't be done by hand anymore, so it has been done on the complete value chain, so taking into account the system, the package, and the device itself. And it needs automatic, let's say, optimization system in order to achieve an optimum. And last but not least, it's not silicon. the wide bandgap semiconductor, they are living from the substrate and not only the quality, it's the size, it's the availability, and at least also the price of this semiconductors. So, last but not least, just an acknowledgement, all these things at Ording have been supported by government, by ECSEL. So a lot of these activities shown here, these activities. And last but not least, it will also be shown that the posters for these activities, we need motivated and good, well-educated people. So when you're interested to work in a field where the market is thriving up very much, very fast, feel free, talk to us, and look where you can bring your potential in. Thank you very much.